Hello everybody, welcome to this week's video classwork of MECA 205. This week we will be talking about sustainability, environmental and social considerations in engineering projects. In our day, the concept of sustainability is used as a basis for the evaluation of projects by many governments, and a strong priority is placed on the environmental and social implications of engineering projects by the public. We will discuss methods for taking account of social, environmental, and sustainability issues. Focus on the social and environmental impact of engineering work compared to the technical and economic aspect of a project was limited before the 1970s. It can be said this was because of the priorities of society at the time. Nowadays, it is accepted that the conservation and management of the Earth's resources and ensuring the needs of future generations is of utmost importance. Engineering is described by Thomas Treadgold of the Institute of Civil Engineers as the art of directing the great force of nature for the use and convenience of man. This was the prevalent opinion of the time, as nature was regarded as a powerful foe to be tamed. Today, we realize that the Earth has finite resources, and we realize that it not only for the protection and conservation of the environment, but also to accomplish a sustainable way of life into the foreseeable future. In the past decades, the concept of sustainable development has been argued widely. The Brundtland Commission of 1978 definition is this: development that meets the needs of the present without compromising the ability of future generations to meet their own needs. In a study conducted by Robert, it has been seen that in nature, self-sustaining systems are usually closed-loop systems that have evolved step by step over time. In the past, when people have developed production systems, they have depended on an open loop once-through use of resources, which results in much waste. To be sustainable, it is necessary to use closed-loop systems. The term sustainability has also been adopted in the business world to signify the principle of social and environmental responsibility. It has been recognized by many business organizations that profits alone do not guarantee continuity of existence for their companies, and that sustainability adds to the long-term viability. Sustainability issues, such as controlling greenhouse gases, are also seen as priority concerns by the investors as well. While it is true that the environment and sustainability have become much more of a focus for concern among people since the 1970s, it would be quite wrong to think that prior to that time there were not problems and concerns. In ancient Greece, some 2500 years ago, Plato lamented the consequences of excessive logging and grazing in the mountainous region of Attica near Athens. Similar concerns were raised 1000 years ago in Japan, where a large sediment delta of eroded granite built up in Lake Biwa due to logging for the construction of a temple. Environmental legislation also dates from ancient times. Julius Caesar prohibited all wheeled vehicles in Rome between sunrise and 2 hours before sunset to improve the situation for pedestrians. This law fell into disuse, and in the 3rd century after Anno Domini, writers complained about the level of noise pollution generated by traffic in the streets. The city of Florence had laws governing the pollution of the rivers Arno, Sieve, and Serchio as long ago as 1477. And in 1810, Napoleon was issuing decrees with regard to the types of industries that could be undertaken in the cities, thus eliminating polluting industries from the centers of cities. In Australia, some of the earliest laws dealt with environmental issues. There were laws to protect the quality of the stream which supplied water for the original settlement, and was prohibited to fell trees within 15 meters of the stream. People were not allowed to throw rubbish into the streams or have pigsties within a prescribed distance of them. In 1839, just 3 years after the city of Adelaide was settled, the state of the Torrens River was so bad that laws were passed to prevent. Among other things, people driving cattle through it. This was the city's only water supply, and yet it was treated with scant regard by many. There are many countries today where this still happens, but as the world becomes more urbanized, there is a need to be aware of the impact of human activity on the state of the planet Earth. Ecological footprint is a measure of humanity's dependence on natural resources. For a certain population or activity, the EF measures the amount of productive land and water required to sustain the current level of resource usage for the production of goods and services and the assimilation of waste required by that population or activity. In 2001, the world average EF was 2.55 global hectares per person, or 30% above the current global capacity. The lifestyle of the average global citizen can therefore be considered as unsustainable. Natural resources are being used faster than they can be generated. The size of an EF can change over time depending on population, consumption levels, technology, and resource use. EFs are measured in global area, hectares or acres. Wackernager et al. Defined biologically productive areas as arable land, pasture, forest, sea space, built-up land, and fossil energy land. The current global biologically productive area is 10.8 billion hectares, of which 21% is productive ocean and 79% is productive land. This represents less than one quarter of the Earth's surface. An individual's resource consumption is not restricted to local resources. The resources used by an individual are from around the world: clothes from China, cars from Korea, and food from many different places. From a comparison of the ecological footprint to the existing biologically productive area, the sustainability of an activity, lifestyle, or population can be determined. Environmental impact assessment is now an integral part of the planning of an engineering project, just as economic, financial, and social issues and technical analysis are. A definition of environmental impact assessment, or IEA, that looks at the consequences is as follows. Environmental impact assessment is a tool designed to identify and predict the impact of a project on the biogeographical environment and on society's health and well-being, to interpret and communicate information about the impact, to analyze site and process alternatives and provide solutions to sift out or mitigate the negative consequences on man and the environment. Environmental impact assessment is thus the means of including environmental factors with both economic and technical considerations at the planning stage of a project. The process of environmental impact assessment identifies the potential environmental effects of undertaking a project. It presents the environmental effects with the advantages and disadvantages of the proposed project to the decision makers, and lastly, forces stakeholders to consider the environmental effects and informs the public of the project while giving them the opportunity to comment on the proposed project. Key elements of an EIA include scoping, which identifies key issues and concerns of interested parties. Then comes the screening, to decide whether an EIA is required based on information collected. Next, identifying and evaluating alternatives, to list alternative sites and techniques and the impacts of each. Then, forwarding measures that deal with risks and uncertainties of the proposed project to minimize the potential adverse effects of the project. And lastly, issues a report called an environmental impact statement, which covers the findings of the IEA. The process of AIA is also present in Turkey. Started in 1993, the environment impact assessment is governed by the General Directorate of Environment Impact Assessment, Permit and supervision, which is a directorate of Ministry of Environment and Urbanization. The process is similar to the other processes worldwide. First, the selection and elimination, then participation of the public, investigation and evaluation of the project, a final decision, and lastly, monitoring and control of the project. The EIA process produces a document called the Environmental Impact Statement, which provides information on the existing environment and predictions about the environmental effects which could flow from the proposal. Whether an EIS to be done in its entirety or whether some other report is warranted by the proposal is decided by government legislation. A number of techniques have been developed to assist in evaluating environmental and social factors. Some of these are listed in the table present. Two of these that will be discussed here are the Battle Environmental Index method and the Leopold matrix display technique. The Battle method or environmental index method is an example of a checklist method. It was first designed for water resource development, but can easily be adapted for evaluation of a variety of types of projects. The principle lies in splitting the environmental impacts into four major categories: ecology, physical chemical pollution, aesthetics, and human interest. The Leopold matrix display technique involves the construction of a large matrix which summarizes all of the environmental and social impacts of a proposed project. Often, this information is given in a quantitative form. One example of this technique is the Leopold matrix developed by Leopold et al. In 1971. One difficulty with the matrix display technique is the difficulty in absorbing all of the information contained in a matrix method. Multi-objective and multi-criteria assessment approaches are also present. In these approaches incorporate economic, environmental, and social aspects and use project evaluation methods that are capable of handling multiple objectives. These methods can make use of qualitative data in an integrated way and have the capability of dealing with trade-offs between objectives. The environmental impact statement usually includes social impacts as well as effects on the physical and biological components of the environment. The following types of social effects may need to be considered for a particular object: distribution of income, population distribution, employment, life, health and safety, educational, cultural and recreational opportunities, national security and emergency preparedness, displacement and relocation, and lastly, neighborhood disruption and intrusion. In theory, it is possible for a government to redistribute the benefits and costs of any public sector project among the various groups in society. This being the case, it can be argued that the role of the engineer or planner is to devise projects which maximize the total net benefit to the community and let the government decide how these benefits and costs will be distributed. However, this redistribution of benefits and costs is often not practicable because of the difficulties in identifying all affected groups and because of the administrative cost of carrying out the transfers. Redistribution of the benefits of engineering projects rarely occurs in practice. Employment. One of the benefits cited by governments when new public works are announced is the effect that it will have on unemployment. A large engineering project may involve considerable employment in the construction phase and also in the operations phase. Some people consider this an achievement in itself. In an economy with little or no unemployment, workers employed on a specific project will be displaced from productive activities elsewhere in the economy. Therefore, the opportunity cost of their labor will be assessed as a cost to the project in the economic evaluation. In such a case, the number of people employed on the project is not a social benefit. In an economy with high unemployment, some of the workers employed on the project may have been previously unemployed. Previously unemployed labor has an opportunity cost to the project considerably less than the wage rate. Many engineering works contribute to saving lives, improving health, or increasing safety in the community. Typical examples are flood mitigation works, water treatment plants, sewage treatment, improved road alignments, grade separation, and coastal protection works. Engineering projects in urban areas may involve the displacement and relocation of some houses and commercial or industrial buildings. A typical example arises from the land acquisition associated with an improved transport link, such as a freeway, arterial road, tramway, or railway. It is common practice for the households or firms displaced to be suitably compensated for the loss of their land, home, shop, or factory. It is often argued that the loss of physical assets is suitably compensated for by the payment of fair market value. However, such an argument ignores the fundamental distinction between value in exchange and value in use. Consider the market for houses of a particular age and quality. If the current market price for such houses is P naught, this may be called the value in exchange of the property. Clearly, all homeowners who are prepared to sell at this price or less will put their houses on the market. However, there are many homeowners who are not willing to sell at the price P naught. To these people, the value in use of the house exceeds its value in exchange. If a road authority were to compulsorily acquire such a house and pay compensation equal to P naught, the homeowner would clearly suffer a loss of utility. Full compensation should cover the value in use of the asset and would usually exceed P naught by a significant margin.